Faraday's law. Faraday found that there is a current in a coil of wire if and if only the magnetic field passing through the coil is changing. This is an informal statement of the Faraday's law. A current can be produced by a changing magnetic field. That is, a current will be produced if B varies over time. So Faraday's experiment, what did he actually do? So what he did was that he had an apparatus similar to this one, and he said that as he closed the switch, the current begins to flow in the primary coil. The ammeter shows a momentary deflection, which indicates a brief surge of current flowing through the secondary coil. The ammeter quickly goes back to zero. Upon opening the switch, another brief deflection of the compass needle is observed. Primary coil produces a B field which goes through to the secondary coil. Only when the B field through to the secondary coil is changing, produced by changing current in the primary coil, does the current flow through the loop. Otherwise, once the B field becomes steady, there is no more changing B field and no more current. So what did Faraday observe? The purpose of the secondary circuit was to detect the current that might be produced by the magnetic field. When the switch was closed, the ammeter deflects in one direction and then returns to zero. When the switch is open, ammeter deflects in the opposite direction and then again returns to zero. When there is a steady current in the primary circuit, the ammeter reads absolutely zero. So Faraday's conclusion: an electric current is produced by a changing magnetic field. It is customary to say that an induced EMF is produced in the secondary current by the changing magnetic field. So later, people did expand Faraday's experiment in this way. So it says current, basically what they did was they put a loop wire and attached it to an ammeter. It was not connected to a battery at any point. But what they found was that if you were to take a magnet and move it towards the current, then there will be a current set up. If you hold it steady, even though that there is a magnetic field present, the ammeter reads absolutely zero. Again, when you make it move away from the magnet, the ammeter starts to read, but it gives you a negative value. So the deflection depends on, or the current being produced in this coil depends on the magnet. It also depends on how fast the magnet was moving and how many loops how many loops do you have to produce the current in. So the basic ways to induce current is A, if you were to move the magnet, or B, if you were to move the conductor. So the magnet is held in place and the loop is moved, again produces a changing magnetic field, or you leave the coil where it is and you move the magnet. Either way, you can produce current. So applications of Faraday's law are far and wide. It is used in ground fault interpreters, it is used in electrical guitars, and it is also used in apnea monitors. So for more details, please make sure that you look it up in the book. Other applications include data storage in patterns of alternating magnetic field, and these are also used in your credit cards. Now, let's talk a little bit about mathematics. So in order to talk about math, let's just quickly go over what flux is. So do you remember Gauss's law from chapter 16? Long time ago. Concept familiar from Gauss's law says that the flux is equals to E dot dA or Q enclosed over epsilon naught. For photons coming from the sun straight down, flux is equals to NVA. Consider the photons coming from the sun straight down through some hoop of some angle theta will give you the flux equals NV dot A. So the magnetic flux can be defined in terms of unit vector area, as the magnetic flux measures the amount of magnetic field proportional to the net number of field lines passing through the loop area if the loop is tilted at an angle theta from the field B. As a dot product, the equation can be written as magnetic flux is equals to A dot B. Please note that the flux contributions can either be positive or they could be negative depending on the direction. So since this is a dot product, we are going to use mathematical formalism for cosine of theta. So flux is given by B perpendicular A equals B A cosine of theta. When theta equals 0, flux will be maximum that flows through. When theta equals 90 degrees, B flux will be equals to 0, as shown here. So flux can be visualized with respect to magnetic lines. The value of magnetic flux is proportional to the total number of lines passing through the loop. When the area is perpendicular to the line, the maximum number of lines pass through the area and flux is a maximum. When area is parallel to the line, no lines pass through the area and hence the flux is equals to 0. So now let's talk about Faraday's law of induction. Faraday's law of induction says the magnitude of the induced EMF in a circuit is equals to the rate at which the magnetic flux through the circuit is changing with time. Mathematically, the rate of change of flux with respect to time will give you E, or electromotive force. In terms of magnitude, E will be equals to delta phi over delta T. EMF is the same thing as voltage. The rate of change of flux is Webers per second. 1 Weber equals 1 Tesla per meter squared. EMF has units of volts. Now let's look at an example. A 40-turn coil of wire of radius 3 centimeters is placed between the poles of an electromagnet. The field increases from 0 to 0.75 Tesla at a constant rate in time interval of 225 seconds. What is the magnitude of the induced EMF in the coil if the field is perpendicular to the plane of the coil, and the field B if the field makes an angle 30 degrees with the plane of the coil? So in this question it says a 40-turn coil of wire, that means N equals 40 and R equals 3 centimeters between the electromagnet, carries the electromagnetic field increases from 0 to 0.75 Tesla at a constant rate, so B is this, at a constant rate in 225 seconds. What is the magnitude of the induced EMF if the field is held perpendicular to the plane of the coil? Okay, so what do I need? I need this value, right? This is what I'm looking for. I'm looking for my induced E field, and Faraday law tells me that this is that. Now my problem is I actually don't know. I know delta T because delta T is given by 225 seconds. I know N, which is given by 40. I don't know delta phi. Okay, so this is what I need to find. But I do know phi equals BA, where B is the field strength and A is the area of the loop. Okay? Now, what is delta phi? Delta phi is equals to change B final minus B initial area. So what does it say? It said that my B field varies from 0 to 0.75. So my B initial was 0 and my B final was 0.75. A. Now how do I find A? Well, it is a loop, right? So the area of the loop is pi r squared. So I will have delta phi equals to whatever this number is, right? Because I have r, and that's given. All I have to do is convert it into meters. Remember to convert it into meters. Once you have that value, you can plug all the numbers in, and I believe you can calculate epsilon, which comes out to be 0.38 millivolts. Okay? Now, part B, it says the field makes an angle 30 degrees with the plane of the coil. Then that means this is the plane of the coil, means that the actual angle will be 90 minus 60. no, it's not, sorry, 90 minus 30. Because we have to find the angle perpendicular to the field, right? This is 30 degrees, so if this is the coil, this is the angle that is given as 30 degrees. But we have to find the angle that's normal to it, which will give me 60 degrees as my angle. So in this case, now this flux, my flux will become B dot A, or BA cosine of 60 degrees. Okay? And then after that, it follows exactly the same route, and we can calculate it easily. And I believe that in this case, the motional EMF will come out to be 0.19 EMF, which makes sense because it has to be less than this. The maximum EMF will be produced when the plane is perpendicular to B field. But this one, it makes sense that it's going to get smaller and smaller because fewer flux lines will flow through.